Welcome to Circle Theorems video. I'm Mr. Lennon. Okay, why is circle theorem so important? Well, circle theorem is very important because in your exam, it's often showed up. And so for CXC, that is, it's about question number 10 that you'll find circle theorems. And so it's very important that you learn the theorems associated with a circle. And it gives you a good option of earning some 15 marks along with other geometry problems. So the objectives in this lesson will be, at the end of this lesson, students should be able to 1. Identify the basic parts of a circle. 2. Know what each circle theorem states. And 3. Show knowledge of circle theorems in their solutions to geometry problems. Circle geometry problems. Okay. First, we want to be able to name the parts of a circle before we can determine the theorems of a circle. Now, this green line all the way around, of course, it tells us that this is a circle, but it's called a circumference. And in the center of the circle, we have this green line, this green dot, sorry. Okay, this is the center of the circle. Now, what's the first line we want to learn about in the circle? Well, a line that passes through the center of the circle, whose ends touch the circumference, is referred to as a diameter. Now, any line whose ends touch the circumference is referred to as a chord. So the diameter is a special chord. Now, what about if we want to half the diameter? In other words, we want to start from the circumference, go towards the center of the circle. Then we will have what is known as a radius. It's a half of the diameter. So we have 2 radii that make up a diameter. A diameter consists of 2 radii. And so here we have it again. What line is this? Well, since it starts from the center towards the circumference, we call it a radius. And it's this length that you use to construct a circle, the radius length. We have another line. Well, so far we're doing a straight line, and it's the end points of this line touch the circumference here and here, and so refer to that as a chord. This is also a chord, again repeating, passing through the center, so it has a special name, the diameter. Now we have a straight line, and this straight line does not pass through the circle, just basically touch it at a point on the circle. We call that point of contact the point of tangency between a straight line that doesn't pass through the circle but just touch it at a point of contact, called a point of tangency. And hence this straight line is referred to as a tangent. Okay, now just want to mention something, so let me just go back a little to a chord. Now this chord, a chord basically, think of this as a pizza or pie. Now if you should use a knife and cut it along this line, this chord, along this chord, this piece, smaller piece here, so just think of it again. I cut this pie, this big pie or pizza, along this line. Then this region here is referred to as a segment. And this big piece is also a segment, but it is a big segment. We call that the major segment. And we call this piece the minor segment. Now this is also a chord. The diameter chord. So the diameter cuts the circle into two equal segments, basically. This segment equal this segment. Okay, just want to mention that. Now, this region here between this radius and this radius, okay, from the center to the circumference. So we have this region in between the two radii is called a sector. And usually when you want to cut a pizza, you cut from the center, and you cut from the center again along another line, and you pull out this piece here. This piece is referred to as a sector. And usually when governments creating their budget, they talk about the tourism sector, the financial sector, the health sector, education sector, etc. Okay, so that's what they usually use. So let's get a little idea there. Okay, so let's look into the theorems now. There are three things you should learn about circle theorems, and we touch on it in the objectives really. What each circle we need to know what each theorem states, and how to identify these theorems when we see them in problems. And third, we should know how to show knowledge of circle theorems in how we answer the questions. And if we can do these three, then we've really got this tricky topic all sorted out. Let's look at the first theorem, circle theorem 1. And here we have this red line and this red line meeting at A and B, point A and B respectively. Now from point A along this line, we call this part of the circumference the arc AB. So moving from point A, going along the circumference to B, that part of the circumference is called an arc. It's a minor arc. And from A going this direction around here, this is called a major arc. Okay, but what we know is that this angle here is standing on arc AB. This angle right here is standing on arc AB. Okay, this angle up there is also standing on arc AB. You notice that? Because what we're noticing, we're taking this line as a leg, and this line as a leg, this red line as a leg as well. This angle has two legs, this red line and this red line. Its legs are standing on point A and B. In other words, standing on the arc AB. And this point, this green point here, is the center of the circle. So this angle here is at the center of the circle, while this angle meets where? On the circumference, a point on the circumference. So there's a theorem for that we need to learn. For example, if this angle here is 40, and this angle down there will be 80. So what is that theorem? Is that the angle at the center is twice the angle at the circumference. So even though we have angle as the center as a theorem 1, it's just brief, but we want to add a few words to it. That angle at the center is twice the angle at the circumference. And that's one theorem we want to memorize. There's a lot of words. Angle at the center of a circle is twice the angle at the circumference. We don't have to put this part subtended by the same mark necessarily. Just angle at the center is twice angle at the circumference is sufficient. But we should note that these two angles are standing on the same arc, or we can say subtended by the same arc. Keep this point in mind. Now this rule can be hard to spot at times, especially when the point A and B that we have a little while moved. Okay, so if we go back, notice what we have point A here and point B here. What if I should move point A a little bit up here, point B, sorry, and then I move point A a little bit up there as well? Would you be able to spot it? Well, let's look at the other one. Now let's get it. So point A was down here, so move it up there. Point B was down here, so move it up there. Now what has happened is that we have created a new angle by moving those points. Okay, so what we're seeing here is this angle here Let's move. All right. Now, if we had drawn a line going across like that, this angle right here would have been 180. Angle on a straight line, 180. But this line has moved further than 180. So from 180 is a straight line. Any more than 180, we call it a reflex angle. So this angle of 230 degrees is what we'll consider to be a reflex angle. It's a reflex angle. Okay, so this reflex angle here, 230 degrees, is at the center still because we move point B from down here to up there. So now we have point B here, and point A was down here. We move it up there. So that's point A. This is still the angle at the center, and it will still be twice the angle here. So what angle is this right there? It's the angle at the center, and this is the angle, still the angle at the circumference. So the same rule applies. What is the answer there? Can you think about it? Let me give you a few minutes to think about it. Not a few minutes, a few seconds, that is. Yeah, that's correct. 115 degrees, a half of the angle at the center. Okay? Must be the center. Now let's see if we can spot this one. Now this angle here, this angle that we have here is 80 degrees. Okay? If I should ask you, what is this angle here? Would you be able to tell me? Would you be able to tell me what that angle is? Give some time to think about it. So we have this angle right here. Can you tell me what angle is this? Well, this is the angle. If you look at it, it says if we move point A and B, so this is point A, and this is point B. We have the angle here. So this angle has both legs, leg standing on A, and this leg standing on B. So this is angle 80 degrees. Do we have another angle standing on the same point A and B? Let's check this angle right here. Let's look at its legs. Standing on point A, and let's check its other leg. Right here, standing on point B. So this angle, by the way, this should be at the center, at the circumference. Okay? It's not drawn accurately. So, but the point though is, this angle here, and this should be right here, center. Okay? So this angle here has both legs standing on the same A, same point B, as this angle right here. This angle 80 degrees, A and B. So the angle at the center must be twice the angle at the circumference because they're both standing on the same arc AB. They are subtended by the same arc. And this is not necessarily easy to spot as mentioned early on. So that's one thing we always have to keep in mind. They're not always easy to spot, but if you focus on the theorems or the principle that is, you're certain to get it. So yes, the angle at the center is 80. The one at the circumference must be 40 degrees. Looks different, but still the center. Now, can you tell me what angle is right here? Can you tell me what angle should this be? Give some time to think about it. Okay, you should get that by now. Okay, so let's call this point A, and let's call this point B. And here we have this angle right here. What angle is this? Yep, you should know what angle that is. So what angle is that? Okay, by now you should get it. Yeah, this is a special case of the same rule we have been looking at all along, but makes a rule in its own right. Yep, this angle is 180 degrees. And so if this is an angle, we're looking at its leg here, standing at point A, and the next leg here, standing at point B. Do we have another angle standing on the same point A and B? Yep, it is this angle right here. This angle right there. And yes, it's 90 degrees. Okay, so the angle at the center, 180 degrees, is equal to, is twice the angle at the circumference. So this must be 90. And this is a new rule. So let's look at it. Circle theorem 2. Angles in a semicircle. Okay, so a diameter cuts a circle in two halves, or a semicircle on top, a semicircle below. And so this angle that is standing on the diameter, or we can say that the angle that is in the semicircle must be what? 90 degrees. Every angle, circle theorem 2, at the center of a circle, okay, at the circumference, that is, at a circle, every angle at the circumference of a circle that is subtended by the diameter of a semicircle is a right angle. A right angle we call 90 degrees. And the reason is because this angle down below here is 180, and the angle at the center must be twice the angle of the circumference. But this is we look at this rule in its own right as circle theorem 2, that angle in a semicircle is 90 degrees. Circle theorem 3, angles in the same segment. Now this angle here and this angle here, what's so special about these two angles? Well, it brings us to circle theorem 3, that angles in the circumference in the same segment of a circle are equal. Why is that so? If you look at it, let's go back a little, is that this angle here, this angle, standing on this, at this point and this point. Okay, so let me just label those 2 points quickly. Get that quickly. So we have this point, point A, right here. And we have another point down here, point B. This angle right here is standing on the point A and standing on point B. And do you notice that this angle here in the same segment is also standing on point A and B? Yeah. And so what do we know about these two angles, therefore? Okay, well, we see they're standing on the same segment. Why is that? Because if you should draw a line, a chord that is, if you should draw a chord, let's take that out quickly. Straight down here. Okay, it should be a chord, it's not straight. Okay, if you draw a chord here, then this chord separates the circle in two segments. This segment here, which is the minor segment, and this segment over here, which is the major segment. So these two angles are in the same segment. And angles in the same segment, according to this theorem, are equal. Okay, so let's look at that again in another fashion. Okay, if you notice, the same two angles that we have here are standing on the same points A and point B. We can also see they are actually in the same segment because this line here separates the circle, cuts the circle in two segments, the minor segment and the major segment. And notice this is the light blue is the major segment. So these two angles are in the same segment, and angles same segment according to circle theorem 3 are equal. Yep, the pale green area is the same segment. So what does that imply? Even the other way around, if we should draw a line here, because circle in two segments, this segment here is minor, and this bigger part is the major segment. And these two angles are in the same segment, so they're equal. So those two are equal. Those two are equal. So these two angles are equal because they're the same segment. If we should draw a line here, a chord here that separate the circle into two segments, the major segment over here are equal. If I should draw a chord here, then this segment down here, these two angles down in the same segment will be equal. And if you think of it, we have two triangles being formed. If this angle is equal to this one, and this one is equal to this one, what about these two angles? All three angles should add to 180. And so these two angles must be what? If you said the same, then you're correct. But we can also think about line properties that when you have two straight lines cross each other, this line here crosses with this line here, then the opposite angles, the vertical angles that are opposite are equal. So this angle and this angle will be equal. But also from the standpoint that the three angles in the triangle must be equal. So if these two are equal to these two respectively, then these two angles will also be equal. Hence the white face. So circle theorem 3 is that angles at the circumference in the same segment of a circle are equal. Angles at the circumference in the same segment are equal. All right, so let's test you now on this. So I'm going to ask you this question, and you're going to try to do some work here rather than just listening to me. So we have this angle right here. So let's call this angle A. Let's call this angle B. Let's call this angle C. Okay, let's call this angle D. Angle A is 30, angle B is 40. What is angle D? What is angle C? You can pause the video, work it out, and then tell me. Okay, so solution, this angle here should be 40 degrees. And the reason is that these two angles are in the same segment. Should you draw a straight line from here to here, this would be a chord that cuts a circle in two segments. So these two angles will be in the same major segment. Should I draw a chord right here that cuts the circle into the minor segment and the major segment, then these two angles down here will be equal. So this must be 30 degrees as well. Now what angle is this? What is this angle here? Can you figure that out? You can pause the video and then come back and tell me. Okay, so if this is 30, this is 40, what is this angle? Well, we know that all three angles must be summed to 180 degrees. So if we have 180 degrees, and the sum of these two angles is 70, how much more do we need to get to 180? Well, we can take the 70 that we have so far, subtract it from 180, and that will give us 110 degrees. So 110 plus 70 give us 180. This angle is 110 degrees. Hence, what is this angle here? Well, if these two angles match these two angles respectively, then these two angles must match. Because sum of angles must add up to 180 in this triangle as well. And also we can look at the standpoint that when two straight lines cross each other, vertically opposite angles are equal. These two angles will be equal, and these two angles here, in it. This angle here equal to the value of that angle there as well. Okay, and so that's about it. Now circle theorem 4. This one states that a tangent is perpendicular to a radius. A tangent is perpendicular to a radius. What does the term perpendicular means? Well, the term perpendicular simply means that the tangent will meet the radius at 90 degrees. When two lines are perpendicular, it simply means that those two lines meet at 90 degrees. So here we have the radius from the center to the circumference. That's a radius. Okay, and there is the tangent that meets this radius. And since they're perpendicular, then the angle formed between them will be, of course, 90 degrees. That was a simple one. Okay, just to make sure you understood that before we move on. What if I should draw a tangent down here? So let's look at it. If I should draw another tangent, okay, it's not gonna be as straight as I want it to be. Should draw another one here. Let's take that off quickly. If I should draw a straight line here, somewhere here, assuming this is a straight line here, this is horrible. Okay, I'm just trying to sketch it now, and then you have a radius going to the center. What angle would you have forming right there? What angle would you have forming there? 90 degrees? Yes, that's correct. Because a tangent will meet a radius at 90 degrees. Okay. Not as nice and tidy as this, but I'm happy that you get the point. And so we can move on. Okay. So then on to the next theorem. Theorem 5, the alternate segment theorem. Alternate segment theorem. So don't get confused with all these theorems. You can always go back to check back. Well, for this theorem, we need a tangent. And so we have a tangent. What else do we need? We need a triangle. A triangle where at one of this vertex meet the tangent. So the vertex of this triangle, so this a triangle has three vertices. One vertex here, another one here, and another one down here. Okay, so I'm going to start so we can organize this one. This one's a little challenging. Usually it's the most challenging one, actually. But some people don't see it that way. They think it's the easiest one. Well, if you find it easy, then that's really good. So we have a point A here. We have point B here. And you have point C here. So what we have is a triangle with one of its vertices, well, one of its vertices meets the tangent at this point, the point of tangency there. So what is this theorem about? Well, let's move on to see what it's telling us. Okay. So that this angle here, that is between the tangent and this side of the triangle, we call it a chord. So the angle between the tangent and the chord is equal to what? This angle over here. So we're still on the alternate segment theorem. Alternate segment or alternate angle theorem. Okay. And this angle here will match this angle here. Okay. Alternate segment theorem. Okay, so let's go back a little. Okay, so let's set it up. It's a little practice. So we have this point here, A. Think of this as angle A. Think of this as angle C. And think of this here as angle B. All right, based on what you looked at a while ago, if I should put an angle, let's change the color quickly. If I should change the color, okay, so well, if I should look at this angle here, okay, I'm definitely gonna need to change that color. Let's use white. So if we look at this angle right here, and let's call this angle 75 degrees. Can we determine the angle B, C, or angle A? Well, based on the alternate segment theorem, we learned that the angle between the tangent and the chord, so this is a chord AB, from point A to point B is a chord. The ends of this straight line touch the circumference, and between tangent and chord is 75. We learned that this angle is equal to the angle in the alternate segment. So if you look at this chord here divides circle into this segment and this segment, this major segment over here. And which angle is in the major segment over here? This angle actually right here. So this angle is actually the 75 degrees. That angle is actually 75 degrees. If you think about it a little, that's where that's coming from. Okay. So now let's look at another point in that. As mentioned before, that's one of the most challenging. So what angle, if we have this angle to be, let's say this is 60 degrees. The angle between the tangent here and the chord AC is 60 degrees. What angle can we determine? Well, again, this chord here, whereas 60 degrees that's between the same chord and the tangent should be equal to the angle in the alternate segment to this segment here. So this segment here, so this chord AC divides the circle into two segments, the minor segment, and everything over here will be the major segment. And so this angle here will be in the major segment. So this chord divides circle into the minor segment, and over here will be the major segment. Okay? So if this is 60 degrees, the angle between the tangent and the chord is equal to the angle in the major segment. So this actually is 60 degrees. Give it some thought and it should be easy to figure out. One way you can think about it is that, look, the angle between the tangent here and the chord here is 75 degrees in this case. So this angle from the tangent to the chord will continue point this direction, 75 degrees. And you can look over here as well. Angle between the tangent and the chord AC is that from the tangent to the chord AC, it will continue to head on this direction. So this is 60 degrees. This is 60 degrees. But I just want you to understand why they say alternate segment. This is because the chord in question divides the circle into two segments, the minor and the major segment. And so therefore, the angle between the tangent and the chord that divides circle into these segments will be equal to the angle not in this segment, because this 60 degrees angle is in this segment, if you notice. This 60 degrees is in the minor segment. So it's equal to the angle that is in the major segment. And the angle that is in the major segment It's not this angle right here, because this angle is barely in the major segment. These angles are barely in this major segment. So we're looking for this one over here. That's 60 degrees. The same concept here. This chord separates the circle into two minor segments and the major segment over here. So this angle here, 75 degrees, based on this chord that divides circle into the major and minor segments. This is in the minor segment. This angle is in the minor segment, and so it's equal to the angle in the major segment, which is right over here of 75 degrees. I hope that was thorough, and so now we can move on. You can go over one more time to make sure you understand. Okay, so that was a mouthful. Now what we have here, now, we have what is known as a quadrilateral, because it's four-sided shape. If you notice, we have four-sided shape. Someone looking at that might think it's a rectangle, but it's not. It doesn't look like it's not a rectangle, but we know it's a four-sided shape, and so it's a quadrilateral. Just like a rectangle is a quadrilateral. In a rectangle, the opposite sides are parallel to each other, and these lines are not parallel. Okay, and they're not the same length either. And so this is definitely not a rectangle, but it's a quadrilateral. It's a four-sided shape. And we just simply call it a four-sided shape because there's nothing to define it as anything different than a quadrilateral, four-sided shape. And quad, four. Okay. Now we call this a cyclic quadrilateral for a reason. Cyclic quadrilateral, all, and it should be ALL, all. Okay. So all four vertices. And so let's go back a little bit. All four vertices must be touching the circumference. All four vertices must be touching the circumference. So if you look at this four-sided shape, this is the vertex here. It's another vertex here of the quadrilateral. This next vertex of the quadrilateral, and this is next vertex of the quadrilateral. Where two straight lines meet, a vertex is formed. So this straight line forms a vertex. So all four vertices of the four-sided shape are on the circumference of the circle. And so what we do, we call that a cyclic quadrilateral. Okay? A cyclic quadrilateral. And there's something special about it, because what we're saying here is theorem 6, opposite angles sum to 180 degrees in a cyclic quadrilateral. Okay, so let's look on to see what that is about. Opposite angles in a cyclic quadrilateral sum to 180 degrees. Okay? And so we're saying that in a cyclic quadrilateral, all must touch the circumference at all four vertices. I'm not sure what that was here. Okay, so this is a little spelling error, so we're going to correct that a little bit. Okay, so what we have here is that in a cyclic quadrilateral, all we can say all four vertices. So I'm going to change all of that. All four vertices must touch the circumference. Okay? So in a cyclic quadrilateral, okay, this quadrilateral is cyclic because all four vertices are touching the circumference. Okay, so in a cyclic quadrilateral, you can make a little note of that. All four vertices must touch the circumference. Okay, we get that point. So we can move on a little bit with that. But this is an important point to note though, because that's not the theorem. The theorem is saying that the opposite angles of a cyclic quadrilateral. So this was just basically helping you to note that it's a cyclic quadrilateral. We say the opposite angles must sum to 180. So we're going to move on to deal with that aspect of it. Okay. So that vertex and that vertex, that vertex and that vertex touching the circumference. And if this angle here is 91 degrees, what is this angle up here? it says opposite angles. So opposite meaning the angles are not sharing the same any of the same lines or legs. This angle and this angle, they're sharing the same line here, or leg here. So they're not opposite, they're what we call adjacent or next to each other. And we have next to this angle is also this angle over here. But opposite this angle is the one that it faces. So this angle is its opposite angle. And the opposite angle to this angle here is the angle over here. Okay, so now we get a point. So if this is 91, what is this angle? And we're told the opposite angles must sum to or add up to 180 degrees. And if you say 79, then you are, well, 79, that's going to be 89. My bad. So if you add 1 to this 89, you get 90. 90 plus 90 is 180. That's correct. All right. Now this is 70 degrees over here. What is this angle here? All right. If you said 110 degrees, then you're correct. Excellent. Theorem 7. Tangents to a circle formed from the same point are equal in length. Tangent to a circle from the same point are equal in length. So here we have a tangent from this point here, and it's going to touch the circumference here, the point of tangency here. We have another tangent from the same point here, right, to the circumference. So what we're looking at is looking at where it actually touched the circumference. We're not looking at this extra piece here. So what you can do is pay attention to this white line. Okay, it's from where the two tangents meet to where one of the tangents touches the circumference, the point of tangency, to the next point of tangency. Okay, just that we want looking at. Okay, so from the point of contact between the two tangents to the point of contact between the tangent and the circumference, those two tangents will be equal in length. Tangent to a circle from the same point are equal in length. And that's, we use two dashes on the white line to symbolize the equality of these two tangents. And that's it for that theorem. Theorem 8. The line joining an external point to a circle of a circle bisects the angle between the tangents. Okay, well, that's a little bit confusing, so I'm going to just look into what it says here. The line joining an external point, so let's look at that. Okay, the line joining an external point to the center of a circle. The line joining an external point to the center of a circle. Okay, so we have the external point here, and we're going to have a line that passes from this point, from this external point. We're going to have a line that is drawn to the center. Okay, so this is point to the center of the circle. So we're going to have a line drawn from the center to the point of contact between the two tangents. And that line that we're going to draw will bisect the angle between the two tangents. This is the angle between the two tangents of 70. Bisect means cut into. So let's see how that turns out. And there we have the line that's drawn from the point of contact between both tangents. Cutted it into two equal parts. Cut the area, the angle between here in two equal parts, going to the center of the circle. So that 70 is divided in two parts now in 35 and 35 degrees. Okay, so now we're going to combine theorem 4 and 8 to help us find the missing angles quickly. Okay, so that's theorem 8. There's going to be 35 here and 35 down here for sure to give us 70. Now, theorem 4 is where we have the radius meets a tangent. Can you remember what angle? The radius meet the tangent at what angle? At 90 degrees. So radius meet tangent at 90 degrees. So how would we find this angle right here? Can you be able to figure it out? Okay, so let's check it out. So what we know so far is that we have that four-sided shape now divided into two triangles. Isn't that so? So we have this triangle at the top with 90 degrees, x degrees, and 35 degrees. What we know is that these three angles should add up to 180 degrees. We have 90 already, so we need 90 more. So x plus 35 should also be equal to 90. So x is equal to 90 minus 35 degrees. And so we can say x is equal to, that's 55 degrees. Okay. Okay, so these two angles should be complementary. In other words, add up to 90 degrees. Okay. And if you wanted, we could have done it the other way around. We could have said 90 plus 35, that's 125. And so we could have said down here, we could have said 180 degrees minus 135, 125, I should say. Okay, so that should be 125 degrees. And that will actually give us 55, 55 degrees. And the reason here is sum of angles in a triangle. That's the reason we're looking at. And so x is equal to 55 degrees. So x is 55 degrees. What angle is this here? Notice it's 35, this is 35, this is 90, this is 90. So x here must also be 55 degrees. And so what we've seen that this line not only divides this angle here into equal parts, but it also divides this angle here into equal parts, 55 and 55. So this angle here would actually be 110 degrees. So if you were asked to find this angle here, let's call it Z, what angle would this angle here be? Now remember, this is the center of the circle. What angle is this over here? For certainty, it looks more than it's a reflex angle actually, because this angle here will be 180. From here to here will be 180, a straight line. And so more than a straight line will be a reflex angle, more than 180. How do we get that? Well, we should recognize that this is actually a circle, right? The center of the circle, we have a circle here. And this part here is 110. 55 degrees and 55 degrees more, that's 110 degrees. And this angle here should add up to, add with the 110 to give you 360. So angle Z will be equal to 360 degrees minus 110 degrees. And angle Z will be equal to 250 degrees. This angle here is 250 degrees. Okay, and that will be our answer there. Okay, and what's the reason for this? And you want to state your answer. You want to state the reason. I don't have enough space here, so you state the reason as angles at a point. Angles at a point sum to 360 degrees. Okay, so that was a nice practice question. All right. So what you got to do for this is to review all theorems and practice applying them in exam questions. Put your mind to it, you can do it. It gets easier every time you practice. Now, we're going to look into an example of an exam question. Now, we're almost done. We're just looking at two examples, exam questions, and we're done. So, the first question. In the diagram below, not drawn to scale, PQ is a tangent to the circle PTSR. PQ is a tangent to the circle PTSR. So that RPQ angle, RPQ is 46 degrees, angle RQP is 32 degrees, and TRQ is a straight line. So what we're going to do, we're going to examine all this information there to make sure we understand what's going on there. I'm going to carry through the thought process as to how you solve a problem like this. So it's not drawn to scale, so if it says it's not drawn to scale, the first we need to know that we cannot use what is known as your protractor. We can't use this device. We can't use this device, this measuring device, this angle device. That's 90 degrees there and 0 and 180 over here. We can't use this device to measure the angles that they're asking us about. Okay, and these are the angles down here they're asking us about, angle PTR. Why we can't use this device, the protractor? Because this diagram is not drawn to scale. So we have to be careful there, trying to use a protractor to draw that. Okay, so let's analyze the other information. PQ is a tangent. So let's look at that. PQ is a tangent. Make sure we understand that. From point P is right here. Point Q is right there. So this line here from P to Q is a tangent. And we can see that because we see the point of tangency right here, where this line touched the circle. Okay, so we understand that. And PQ is a tangent to the circle PTSR. So we have the circle that's described as as circle P moving right around to T to S to R and right back around. We don't really call this the letters twice. So we just call it circle P T R S right around. Okay? All right. Next point is that angle R, this means angle, symbols mean angle. Angle RPQ is equal to 46 degrees. Let's look at that. So moving from angle R to P, sorry, we're going to move from line R to P, then from line P to Q. And that creates an angle, a turn. So angle RP, line RP I should say, we move from R, which is right there, to P. And now we're going to turn, so we move from R to P. Now we're going to turn to Q, right down there. So we had R now, moving right on to P, and turn to go down to Q. Okay, so this angle they're looking at is right here. This angle. Okay, so this angle here is 46 degrees. Angle RQP, start from point R, go to Q, down to Q, and then go turn at P. Turn to P. So this angle they're looking at is right here, which is 32 degrees. This also told us that TRQ is a straight line. TRQ is a straight line, so it's not an angle. So if you move from T to R, then R to Q, you're not going to have any turn moving from R to Q. So it's a straight line right from T to Q. So let's get it from T, moving on, for this T, move from T to R, straight on to Q. There's no angle symbol like in this case right here. Okay. So we're asked to calculate, let's identify the angles we want to calculate. Angle PT, this is one. So right there. Angle PTR. So from P to T to R. So looking at this angle right here. Do you want us to calculate what angle is this right there? Okay, so what angle is that? Okay, so let's analyze what we have so far. Well, what we do notice is that we have a cyclic quadrilateral. Okay, we have T, quadrilateral T, S, R, P. All four vertices are on the circumference. It's a quadrilateral, so we know that the opposite angles will be equal. So we know that angle S, we know that angle S plus, we know angle S plus angle T, this angle right here, and this angle right here will be equal to 180. What else we know? We know angle R plus angle T down here, angle R plus angle T is also equal to 180 degrees. I want to say angle T, I'm not talking about this little angle right there. Talk about the entire angle there. So looking at that now, we need to find angle PTR. PTR. And how are we going to do that? So we need to look at what we have so far. Okay, what I noticed that this is actually what? A tangent. It's a tangent, and here we have this angle. This angle 46 is between a tangent PQ and between the chord PR. So this 46 degrees is between a tangent and a chord. And what did we know about a tangent and a chord? Okay, from a prior learning we learned that angle between a tangent and a chord is equal to angle in the alternate segment. Okay, so this angle here, from here to here, is same as this angle here. This angle between the tangent and the chord is equal to the angle in the alternate segment. So this angle here, from the tangent to the chord, is pointing right down here. So that's 46 degrees. So our answer to that is going to be 46 degrees. Okay, so let's tie this up a little bit. Okay, so the angle between the tangent and a chord, this is tangent, the chord, 46, is equal to the angle in the alternate segment. So this chord creates this segment here, the minor segment. This chord PR I'm talking about, and this is the major segment. Okay, and so this angle here is actually standing on the same chord P. This angle I'm talking here is standing on the same chord P and the same point P and the same point R. So this angle is standing on the chord P R, in other words. So this angle is equal to the angle that's between that same chord and the tangent. We call it the alternate segment theorem. Okay, so it's equal to 46 degrees. I think I need to write that a little better. So equal to 46 degrees. And the reason is alternate segment theorem. Next one, angle TPR. Angle T. So angle T going to P, and you turn at R, and that should be right here. What is this angle right here? Angle T P R. So looking at this angle right there. What is that angle? Okay, so we need to take a little time to think about that. We have, if you look at this angle here, it's a part of a triangle for sure. It's part of a triangle. Yeah. And so we need to do a little thinking about it. But what I can do so far, well, if you look at this, what we have outside here, what I notice is that we have a triangle outside here. Okay, we have a triangle. We have triangle P R Q. So if I should draw that a little bit, I should draw a triangle P. Let's look at it. Triangle P. All right. This is 32 degrees. This one is 46 degrees. This is P. That's Q. And this is R down here. I can find this angle in it. How do I find this angle? Triangles in a triangle should have 180 degrees, so I can find this angle here. This angle here, in other words. Follow me? I'm right down here. Okay. So what's this angle? Well, if I add up 32 plus 46, I'll do get 78. And then I'm going to take that from 180 degrees, and that should give me 102 degrees. This angle right here is 102 degrees. Okay. Now this angle here is 102 degrees. Okay. And the sum of angles in a triangle. That's my reason. So you put your reason as sum of angles in a triangle. This angle here, so I can find it. If I find this angle here, then I can find this angle here. Okay, so what I will say is in my solution sheet, I'll actually have angle P RQ, angle P RQ from P to R to Q is equal to 102 degrees. And my reason is sum of angles in triangle. Sum of angles in a triangle. Okay. Of course, you're going to write it out in your exam a little bit better. Okay, so this, all right. So now that I found this angle 102, I can find angle PRT. Angle PRT. Okay, so this angle here is what? Is equal to 108 degrees minus 102 degrees, and which gives me 78 degrees. Okay, that will give me 78 degrees. And the reason for this is angles on a straight line. On a straight line. Okay, if you're not be able to see this properly, just notice this angles, angle symbol, angles on a straight line. Why am I saying that? Because this angle here is actually in a straight line with this one over here. And if this is 102, then this is difference. This is 78 degrees. So the difference between 180 and 102 is 78. So angle PRT is 78 degrees. So what we have now is this. So if we have what we have so far is, let's get it. I mean, there are many ways we probably can find certain answers. This is the way I've looked at it so far. So I have 46 degrees here for T, angle T. Angle R, referring to this angle piece here, this little piece here, that's 78 degrees. And so what is this angle here? And that's the one they want to find, angle P, which is T, P, R. That's difference, isn't it? That's going to be 180 degrees minus the sum of 46 plus 78 degrees, which equals to 180 degrees minus, let's write that out quickly. That's going to be 80, that's 120, 124. Okay, 124 degrees. That should give us 30 is 50, 56 degrees. Okay, let's try that. 6 plus that is 130, and 130 plus 50, 180. Yeah. Okay, so this angle here should be 56 degrees. Okay, so we found that angle here, P, 56 degrees. And don't forget our reason for this is sum of angles in triangle. Sum of angles in a triangle. This is the angle symbol. This is the triangle symbol. Okay, so now we're down to TSR. T to S to R. So we have to find this angle here. From T to S to R. Remember earlier on what was said is that this is a cyclic quadrilateral. Okay, so cyclic quadrilateral. We have a four-sided shape from T to P to R to S. All four vertices are on the circumference. And so the opposite angles add up to 180 degrees. Okay, so angle TSR is equal to 180 degrees minus 56 degrees. All right, and that should be equal to 124 degrees. And the reason for this is that this is the opposite angles of a cyclic quadrilateral. Okay, you can read that, but we can also says sum to 180 degrees. Opposite angles of a cyclic quadrilateral. I think we could stop there, but sum to 180 degrees is also fine. And so this angle here is 124 degrees. Okay. So it takes a little bit of thinking on our part to figure it out. You don't have to put these values in really. It's on your answer sheet. You want to be able to put these answers down, but state the reasons. So if you notice, beside every answer, there's a reason. And even if you didn't just put the answer here, at least I showed the working over here as to what I was doing. Okay, all right, so that's for that. And let's look on to the next question and final question on the circle theorem that I'll be showing you. Of course, you can always practice some extra questions. Exam question 2, the final one. So the diagram below, not drawn to scale, shows a circle with center O. So we have to keep in mind they have a center. This line, the line DCE, is a tangent to the circle. Let's check it out. So we have D to C to E. Okay, so it's indeed a straight line. Is a tangent to the circle, and yes, it is. Point of tangency. Angle AC is 48 degrees. Angle from point A to C to point E is 48 degrees. So we have a turn there. So looking from point A going on to C, and we're turning at C to E, and that angle here is 48 degrees. The angle there is between a tangent and a chord. And angle OCB is 26 degrees. Angle O, this angle O here, as far as point O, and this point C, I'm going to turn to B, get the angle of 26 degrees. Okay, so let's look at this question now. Seems pretty easy. And so what we have there is we have to identify what we've seen so far, and that will help us a lot. Okay, so we're seeing a radius, and a radius meets a tangent. And we know that rule, that a radius meets a tangent. So we know this angle right in between here should be 90 degrees. All right, so we know that this is a radius. From the center of a circle to the circumference is a radius. And this is a tangent, and a radius meets a tangent at 90 degrees. So this should be 90 degrees there. So we can put a little right angle there. And obviously on this side is also a right angle because we have a radius, sorry, and then a tangent. So we know this is also over here, should also be 90 degrees. So the angle between this radius and this tangent is 90 degrees, and the radius and this tangent is 90 degrees over there. Okay, so now we found that out. So we know this angle, we can find this angle between here easily, as well as this angle between here. Okay, so this should be 90 degrees in total. So this should piece to be the difference between 90 and 48. This piece in between here, because all the way down should be 90 degrees. What other things should we note as well too? All right, so we know this is the chord that divides the circle in a major segment and divide it in also a minor segment. Okay, and since this angle between this chord, chord 48, between the chord and the tangent here, this angle of 48 degrees is in the minor segment, of the chord AC. So the angle in the alternate segment, the major segment that is over at B, should be the equal actually. Angle in the minor segment between the tangent and the chord is equal to the angle over there in the major segment at the circumference. That's the alternate segment theorem. What else do we see in this that we actually know? Well, what we're seeing here is the angle at the center. Angle at the center is twice the angle at the circumference. So we say angle at O, whatever angle that's going to be, should be twice the angle at the circumference at B. And since if we figure out what B is, we double it to find the angle at O, since angle at O is twice it. Okay, so let's go on to start solving the problem. So that's a little review as to what we know so far, we studied so far. So here's what angle ABC, going from angle A to B to C. So I guess they want us to find this one first. Angle at the circumference. Okay. Now, how are we gonna find that? Well, it should be noted that the angle at the circumference there can be found by looking at what we looked at earlier on. The angle between the tangent should come back to your mind. Between the tangent and the chord ABC is 48. So the angle that points over there, the angle in the minus segment, is equal to the angle over there in the major segment. So this is going to be 48 degrees as well. Okay, so that's 48 degrees. And the reason for that is uh, alternate segment theorem. Alternate segment theorem. Okay, so that's 48 degrees. Angle AOC. So angle A to O to C. So this angle here. And now we notice that angle B has both legs standing on AC, and angle O at the center has both legs standing on the same AC. So angle at the center, therefore, is twice angle at circumference. This angle should be 96. Okay? It should be twice angle ABC, in other words. So it should be 96 degrees. What's the reason? Angle, angle at center is twice angle at circumference. Forgive me on my writing. And the instrument is kind of slippery. Okay, so angle AOC is twice the angle ABC. Angle at center, twice angle at circumference. BCD, angle BCD. So when I find this angle here, angle BCD, right between here. B to C to D. This angle right there. We already established that this angle um, from the radius right down to the tangent is 90 degrees. Because the angle in between, the total angle between a radius and a tangent is 90 degrees. So if we have part of it, which is 26, the next part of it should be complementary to 26 to up to 90 degrees. So that actually is 90 degrees minus 26 degrees. And so that should give us a 30 from 90, that's 60. And add on 4, that's 64 degrees. Yeah. And so that's going to give us, yes, 64 degrees. And the reason for that is radius meets tangent. Radius is perpendicular to tangent. Same thing as saying radius meets tangent at 90 degrees. They're perpendicular, in other words. Okay? They're perpendicular to each other. Okay, so now we found that. So this is actually 64 degrees. Next one, angle BAC. Angle BAC. So we look for this angle right here. From point B to point A to point C. So looking for this. So we move from B to A, or drive it on to C. So looking at this complete angle here. What is that going to be equal to? Okay, so that might be the only challenging one they can think of. Well, so far we know this entire angle should be, well, it's not really challenging. In fact, it should be actually easy. The angle between the tangent and the chord. If you look it over here, so angle tangent DCE, I'm looking at chord, we're looking over here, chord, right, chord BC, okay, angle between it is 64 degrees, and we're noticing that chord BC is pointing towards angle A. right? Look at it, points at angle A. So this segment over here, so chord BC cuts the circle into two segments, the minor segment, and the angle in the minor segment is 64, and the angle in the major segment over here at B should also be 64 degrees. So angle BAC is equal to 64 degrees. And this is alternate segment theorem as well. Okay, now we're down to angle OAC. Angle OAC. Angle OAC. Now to find angle OAC is a little easy as well too. So let's look at it. I'm going to draw a circle down here. Okay, I think I need to do that a little better. Better job at that. Okay. So what we had there, okay, everything just disappeared. Okay, so let's go back over this again quickly. This was angle. This was 48 degrees. We said this angle over here is 48 degrees. This one here is going to be 96 degrees. 48 degrees because this angle between the tangent and the chord is 48. And so the angle in the alternate segment to this minus segment 48 degrees, which is in 48 degrees. The angle in the minus segment here is 48. 48. And so this angle over here is in the major segment, so it's 48 degrees. So we call this the alternate segment theorem. And this one is angle at the center is twice the angle at the circumference, so it's 96 degrees. Okay, so this one is 48. We already put a reason early on. And this one is going to be 96 degrees. And this one, BCD, B to C to D, this angle right here. Well, this entire angle is 90 degrees, angle between a radius and a tangent. So you have to state it. We have to give our reasons. So this is going to be, 90 degrees minus 26 degrees, and that angle should be 64 degrees. Angle BAC. Let's move from B to A to C. Now this angle, so this angle here is 64. The whole thing is 90. 64 plus 26 is 90. Now BAC, this angle right here, is what? Well, if you look at it, this angle here in this segment, because this is chord BC. So looking at this segment here, in the minor segment is 64 degrees. And so the angle that this chord subtends at the circumference is equal to the angle between the same chord and the tangent in the minor segment of 64 degrees. So the angle that this chord subtending in the major segment is the same as this one in the minor segment. So this is 64 degrees. This angle right here. So angle BAC is 64 degrees. And of course, put the reason. Alternate segment theorem. So this one is alternate segment theorem. Alternate segment theorem. And this one was also alternate segment theorem. Okay. This one here was angle at center. Angle at center. Twice angle at circumference. And this was what? Radius. Radius meets tangent at 90 degrees. They're perpendicular. And OAC from O to A to C. So what I'm saying, we're going to draw a circle. Okay, and we have a center of the circle. What we call this line a radius. We also call this a radius. Now these two lines have the same length. So when we draw a straight line going across like that, what is formed is an isosceles triangle. Okay, I think I need to do that a little better somewhere down here. Okay, so what is formed there is this side and this side here. They're equal because this is a radius and a radius. All radii in a circle are equal. So what is formed there is an isosceles triangle. An isosceles triangle of this length is the same. That means the base angles will also be the same. Okay, so what we have in this circle here is that the angle at the center here is 96 degrees. So let's look at it. So let's draw this bigger. 96 degrees. And so, and we know that this length, same as this length, because this is a radius and this is a radius. So they are the same length. So this angle here must be the same. And so how can we find that? How could we find that? Well, if that's the case, a second, let's tie this up a little bit. I'm sure you already start working it out already, which is really good. Okay, that give you some time to finish working it out. And so if we have an isosceles triangle with one angle being 96 degrees, what are the other two angles, which are the base angles? If the base angles, this angle here is equal to this angle here, and we know all three angles must add up to 180 degrees, then the base angles must be equal to what? So let's write that out. So we have 180 degrees, and we subtracted 96 degrees. This 96 degrees is not the base angle. It's just the other angle, the bigger angle. We'll take it away from that, and that will leave us with 4 and 10 to this 17, 174 degrees. Yeah. So, okay, this is awful. So, no, what am I doing here? So 6 from that, take away 7 here, and 6 from that give us 10 give us 4, and then we have 9 from 7, 9 from 17. Let's give us so I've made my mistake right here. Okay, 9 from 7 give us 8, so that's 84. So these two angles must add up to 84 degrees. Because this is 96. Okay, that's 96 degrees. To get 84, okay, to get 180, we have to add 84 to 96. Okay, and that will give us our 180 degrees. So these two angles must add up to 96 degrees. So I'm sorry, my bad, 84 degrees. So what we're going to do, we're going to take the 84 and divide it in two parts, and that will give us 42 degrees. So this angle here is 42 degrees, and this angle here is also 42 degrees. So angle OAC is equal to 42 degrees. Now this is a real long way of doing it, because we could have done that easier by just simply looking at this side. This is a radius, and this is a radius. This is a tangent. So the angle between the radius, I'm moving from the radius to the tangent, that's 90 degrees. And so if this is 48 so far, the next piece must add on to give us 90. So we're gonna find OCA first. OCA, angle OCA, which is equal to angle OAC, because these are base angles of an isosceles triangle. Base angles of isosceles triangle. Right? And they're equal. So once I find OCA, and OCA, angle OCA is equal to 90 degrees minus 48 degrees, and 50 from 90, that's 40 plus 2, that's 42. And therefore, angle OAC is equal to 42 degrees. Okay, so we could have done that the other way around as well too. We don't even have to trouble the fact that this is an isosceles triangle. Well, I mean, we don't have to actually go in this route, taking 96 and divide it by 2. But once we find one, we can find the other one. But we have to consider that, yes, that it is an isosceles triangle, because this is 42. Then we can say, yes, the other angle is also 42. Okay, the last one is OAB, angle OAB. Okay, now that should be simple. Angle O to A to B. Since we found angle OAC to be 42 and the entire angle BAC to be 64, then these two pieces must add up together to give you 64. In other words, if this entire angle here is 64 and this piece is 42, then what is this piece here that they're asking us for? Angle OAB. So we can find angle OAB quite quickly by putting 64 degrees minus 42 degrees, and that will be equal to what? Okay, so that's be equal to 2 from 4 give us 2, and 4 from 6 give us 2, 22 degrees. Okay, and that's about it. Okay, all right. Thank you for watching. This was a long video and I'm tired, but hopefully it was helpful. Okay, so hope you enjoyed taking down the examples. And please send us your feedback by emailing us at lenonmaths.com.